So welcome to lecture number 19, Fundamentals of Transport Processes, where we were looking at transport in curvilinear coordinates, where the coordinates are not straight parallel lines. Initially, in the first part of our discussion on unidirectional flows, we had considered problems in Cartesian coordinate system, where the x, y and z axes are all perpendicular to each other. The unit vectors are constant, they are independent of position, and we solved the equations for the flow past a flat plate, the temperature gradient due to a heated plate, both under steady conditions, unsteady conditions, with and without velocity fields and so on. The problem with that is that it is applicable only when you have surfaces that are planes, so that you can put a boundary at a coordinate say z equal to 0. Very often we come across systems where the surfaces, the bounding surfaces are not planes. For example, the flow in a pipe, which we will see a little later, the surface is a cylinder, and if we try to express the surface of a cylinder in Cartesian coordinates, we get an equation of the kind x square plus y square is equal to r square, where r is the radius of the pipe. And it is very difficult to enforce boundary conditions on those surfaces because they are not at constant values of the coordinate. Therefore, we look at other kinds of coordinate systems where the bounding surfaces are at constant values of that coordinate. In the particular case of the flow around through a pipe, for example, you would consider a surface where the surface of the pipe is at a fixed value of radius. Okay. In this particular case, the surface of the pipe is at r is equal to capital R, at a fixed value of the radius. So, I will take a coordinate system where I have an axial coordinate, which is basically the z coordinate in this figure, which is the distance along the length of the pipe. That is one coordinate. The second coordinate is the distance from the axis of the pipe, that is the r coordinate. Okay. So, r basically tells you how far a point within the pipe is from the axis, the perpendicular distance. And of course, there is a third coordinate. You need 3 coordinates to specify any position in 3-dimensional space, and that third coordinate is the angle that the radius vector makes with any particular axis. Usually, it is taken as the x axis. The angle that the radius makes with the x axis is given by the coordinate theta. Note that theta is dimensionless. R has dimensions of length, z has dimensions of length. Okay. So, how do I relate r, theta and z to x, y and z? It is clear that along the x, y plane, right, the distance made by any position to the x axis is given by the coordinate, is given by the radial coordinate. Okay. So, therefore, if I had some position on this surface at a distance r from the origin, I just take the projection of that onto the xy plane. The distance of that projection is r, the angle it makes with the x axis is theta. Okay. So, it is obvious that x is equal to r times cos theta, y is equal to r times sin theta. Okay. And z of course is the same. The axis of the cylindrical coordinate system is identical to the z coordinate in a Cartesian coordinate system. The other way, r is the distance from the z axis. So, it is square root of x square plus y square, and tan theta is equal to y by x. So, that is the relation between r theta and x y. Okay. So, in order to analyze transport in a cylindrical coordinate system, we have to take a differential volume which is bounded by surfaces of constant coordinate. Okay. If you recall, when we did the analysis in a Cartesian coordinate system, we took surfaces to be planes. Okay. We took planar surfaces. Okay, we took planar surfaces. So, the front and the back were at constant values of x, the left and the right were at constant values of y, the top and the bottom were at constant values of z. In a similar case, in the cylindrical coordinate system, we take two surfaces at constant r and r plus delta r. These are of course cylinders, cylindrical cross sections. One has radius r, the other has radius r plus delta r. And then there are two surfaces at constant z, one at z, the other at z plus delta z. Therefore, in this case, the differential volume is an annulus of thickness delta r and height delta z. In this particular case, we have assumed that there is no variation with respect to theta. Everything is the same as you go around the z axis, so long as your distance from the z axis remains the same. Okay, so, there is no variation with respect to theta, and that is why we could choose surfaces at just r and r plus delta r and z plus delta z. And once you do that, you get a differential equation for the conservation of mass, momentum and energy that has this particular form. Okay, the differential equation that you end up with has this particular form. This is of course in the absence of flow, and note that this is different from what we got for a Cartesian coordinate system. In that case, we got on the right hand side alpha times d square t by dz square. In this case, it is more complicated, and as I explained in the previous class, the reason is because the surface area is changing with radius. I have cylindrical surfaces. Obviously, the surface area of that surface is going to depend upon the radius of the cylinder. That changes as I go from r to r plus delta r. So, even though the flux may be a constant, if the area changes, there is going to be a change in the total amount of heat or mass flow, and that accounts for this more complicated form of the differential equation. So, last two lectures we looked at problems involving similarity solutions and separation of variables in cylindrical coordinate system. Okay. In a cylindrical coordinate system, we found that for the separation of variables, okay, we cannot impose a boundary condition on a surface. We have to impose it on a wire of infinitesimal thickness. You cannot enforce a temperature boundary condition on this. The boundary condition has to be of the form total heat coming out of this wire is given by a particular value q in this case, or the total mass coming out is given by a particular value in the case of a mass transfer problem. If the total heat coming out is a constant value, the wire is of infinitesimal thickness, and therefore, the flux has to go to infinity as the radius of the wire goes to 0. The flux goes to infinity, the temperature also goes to infinity, but the total amount of heat coming out is a constant. So, that is a feature of these problems. This is called a line source in 3 dimensions. In the case of this line source, you cannot specify the temperature at the source or the heat flux at the source. You have to specify the total heat coming out of the source. And if you do that, you can then get a similarity solution. Okay. And the similarity solution has the form as this form. Okay, where there is a constant in that, the constant C we had determined from the condition on the total amount of heat coming out of the surface. Note that the temperature goes to infinity in this case, because I have a factor C by psi prime. Psi prime is in the denominator. As psi prime goes to 0, I am integrating over a divergent quantity. So, the temperature actually goes to infinity, but nevertheless the total amount of heat coming out is of course a constant. Okay. So, this is a limiting case where the thickness of the wire is small compared to the other length scales in the problem. In that case, I can consider the wire as a line source. And then we had looked at the heat transfer to a finite cylinder. We had done this pretty quickly in the last lecture, so I will briefly review this before I go into the topic for the present lecture. Okay. What it is a cylinder. Okay. We will assume for the moment that it is of infinitesimal length in the z direction. It is finite only in the radial direction. The cylinder of temperature T1 is dipped into a fluid which is originally at the temperature T0. The fluid can be considered as an infinite bath, so that the temperature of the fluid does not change appreciably as the cylinder is cooling. Okay, you can consider that the mass of the heat bath is large compared to the mass of the cylinder. So, the decrease in temperature of the cylinder does not appreciably increase the temperature of the bath. So, I have to solve this problem, the heat transfer problem, within the cylinder to see how it cools as a function of time. Initially, T is equal to T1 everywhere within the cylinder. At time T is equal to 0, the cylinder is dipped into the bath. Therefore, at time T is equal to 0, the temperature on the surface of the cylinder is equal to T0. And as time progresses, the cylinder cools. Okay. So, in this case, since we have a cylinder of finite radius, one can scale the radius r by the radius of the cylinder itself. Okay. And if you scale the radius r by the radius of the cylinder itself, the scaling for the temperature is what we had got previously. The scaling for time is what we had got previously. The scaling for time is basically the time it takes for diffusion to take place over a distance of r, where alpha is the thermal diffusivity. One could equally well solve this problem for mass diffusion. In that case, we assume that the concentration within the cylinder is C1 at time t is equal to 0. It is dipped into a bath with concentration C0. At long times, because of the diffusion from the cylinder to the bath, there is going to be a constant concentration everywhere. Okay. So, we had got the thermal balance equation written in terms of the scaled temperature, the scaled time and the scaled distance. Okay. And the boundary conditions, note that this is second order differential equation in R, it is first order in time. So, you need two boundary conditions, one initial condition. This cylinder, however, has only one boundary. That boundary is at R is equal to capital R. Okay. At that point, we require that the temperature is 0. Okay. The scale temperature has to be equal to 0 because T is equal to T0 at R is equal to capital R. How about the other boundary? Okay. I had argued based on physical considerations, okay, that the other boundary condition should be that R star, the other boundary condition should be that at R is equal to 0, dt by dr has to be equal to 0. Let us briefly review that argument. Okay. This is my cylinder, this is the center, okay. And as a function of distance r, if I plot the temperature, okay, let's plot a little better. If I plot the temperature as a function of r, let us assume that the temperature gradient is not 0 at along the axis. That means that if I plot the temperature as a function of r, the temperature profile will look something like this. Okay. It could have a negative slope, it could have a positive slope, it depends on the situation. But let us just assume that the slope is non-zero. note that there is nothing changing in the theta direction. So, as you go around the cylinder, there should be no change in the temperature. Okay. So, that means if I go on the left hand side, the temperature profile should be an exact mirror image of this one. It should look something like that. Okay. But a temperature profile like this does not have a continuous slope at the axis itself, because from the left hand side it comes up like this, the slope in this case is positive. From the right hand side it comes up like this, the slope is negative. Similarly, as I go all the way around the cylinder, I will get different slopes at different locations. As I approach the origin from different positions around, if the field is axisymmetric, I will get different slopes from each direction. Different derivatives dt by dr will be different for each location that I calculate the slope from. Okay. The only way that the derivative can be single valued is if it actually comes to 0 at the center. Okay. If it actually comes to 0 at the center, the slope is 0 no matter where I approach it from. Okay. So, the symmetry of the configuration itself dictates that this dt by dr is equal to 0. Okay. Because if it is not 0, you are getting different slopes from different directions and the derivatives are different. That means that the heat flux is equal to k times dt by dr. So, the flux is actually coming out different in different directions from the center in different locations. If I had a heat source at the origin, of course, I could have a non-zero slope at the origin, because I could have heat flux coming out in all directions. But this is just a cylinder with no source in it. Therefore, the slope has to be 0 at the origin. Okay. So, that is a symmetry boundary condition. It emerges from the fact that the cylindrical coordinate system is axisymmetric around the axis. As you go around the axis at different locations, you should get exactly the same temperature field. That implies that dt by dr has to be equal to 0 exactly at the axis. And we had an initial condition that t is equal to T1 at time t is equal to 0 for all values of r. Okay. That means that T star is 1 at at the initial time t is equal to 0. So, as I said, by automatically in this particular case, you get homogeneous boundary conditions on both boundaries. T star is equal to 0 at r is equal to 1 and the derivative is 0 at r is equal to 0. The only forcing is at initial time T star is equal to 0 when capital T star is equal to 1. That is the requirement for our separation of variables procedure. As I told you, in separation of variables, in order to get discrete eigenvalues, those were eigenvalues were beta n is equal to n times pi in the previous problem. To get discrete eigenvalues, you require that the boundary conditions be homogeneous and then there is a forcing at initial time. Those properties are already satisfied by the solution of this equation. So, we did the separation of variables procedure, separated out into a function of r, a function of t, and we got differential equations for r and for t. Okay. So, this is the differential equation for r, where beta has to be a constant. We took the constant as negative because we required that theta has to go to 0 as t goes to infinity. Only if the constant is negative will theta decrease exponentially as t goes to infinity. Okay. And that negative constant was inserted into the equation for r, and we got a differential equation, okay, whose solution, this differential equation is called a Bessel equation. It is called a Bessel equation, and the solution of these are Bessel functions j n and y n. In this particular case, for this particular equation, n is equal to 0. Okay. So, the solutions for the equation that we got are C1 j naught of r and C2 y naught of beta, I am sorry, C1 j naught of beta times r and C2 y naught of beta times r. As I told you, these are similar to the sine and cosine functions. They are also oscillatory in nature, but they decay as x power minus half as the argument becomes large. Okay. And at r is equal to 0 itself, j naught is finite, y naught goes to minus infinity. Okay. Therefore, if the temperature has to be finite with 0 slope, the coefficient C2 has to be equal to 0, and we just got the solution as C1 times j naught of r plus. Okay. And then we have the boundary conditions T star is equal to 0 at r is equal to 1. Okay. The j naught of course satisfied the 0 slope condition right at the origin. Okay. J naught satisfies the condition that the slope has to be equal to 0 right at r equal to 0. But we have another boundary condition, which is that r is equal to 0 at r star equals to 1, or C1 times j naught of beta has to be equal to 0. Okay. So, C1 times j naught of beta has to be equal to 0. That means that beta has to have, it cannot have any value. Okay. It has to have a particular value in such a way that this function j naught, okay, is equal to 0. This is the function, I am sorry, this is y naught. So, this is the function j naught. Okay. This function j naught has to be equal to 0. So, j naught of beta has to be equal to 0. That means that beta has to have a set of discrete values. Okay. This is the analog of the values n pi that we had got for the flow past for the transfer from a flat plate when we did separation of variables in a channel between two plates separated by distance h. In that case, we got the eigenvalues as n times pi. These discrete eigenvalues are analogs of that. They are not exactly n times pi, and they are not exactly separated by equal distances, but they are still discrete values that satisfy j naught of x is equal to 0. Okay. And therefore, you can write the solution. I gave you the first few set of these solutions, beta 1, beta 2, beta 3, beta 4, and therefore, a general solution can be written as the summation, okay, over all of these discrete solutions, okay, of j naught of beta n times r times e power minus beta n squared times t. Note that you have the same exponential decay that we had in the transport from a flat plate. Okay. The coefficients Cn of course have to be determined from the orthogonality conditions. Okay. The orthogonality conditions for the Bessel functions are slightly different from the orthogonality conditions for the Cartesian coordinate system for the sine and cosine functions. Okay. In the case of the sine and cosine functions, we had integral dz of the two functions is equal to delta mn. Okay. In the case of the Bessel functions, you have integral of r dr, okay, times j naught of beta m r, j naught of beta n r. This is integral of r dr is once again a delta function. It has a non-zero amplitude. In this case, it is called j1, where Bessel function of order 1 of beta n the whole square. Okay. So, using this, you can get back the solution. You can calculate each and every constant Cn. Okay. So, I have the requirement that at T star is equal to 0, the temperature has to be 1. Therefore, summation Cn times j naught of beta n r has to be equal to 1. And I enforce the orthogonality condition the usual way. Multiply by j naught of beta n r times j naught of beta m r and integrate from 0 to 1. Okay. This is equivalent to, in our previous case, we wrote that T star is equal to summation Cn Jn e power minus n minus beta n square T star at T star is equal to 0, T star is equal to 1, which means that summation Cn Jn, okay, is equal to 1. How do I get the constants? I take the inner product. Jn comma Jm is equal to inner product of 1 with Jm. Okay. Therefore, this summation n is equal to 1 to infinity Cn times half J1 of beta m the whole square times delta mn is equal to 1 comma Jm. Okay. So, therefore, Cn times delta mn is non-zero only when n is equal to m. So, summation Cn times delta mn is just going to give me Cm. So, I will get Cm times half J1 of beta n whole square is equal to this, which is integral r dr J naught of beta m times r. And from that I can determine each and one of these, every one of these coefficients. There is an infinite number of such coefficients, but it should be noted that the contributions to the higher order terms decays. Okay. The contribution due to the higher order terms actually decays exponentially. Therefore, as beta n increases, this decays exponentially in time. Therefore, like in the case of the heat transfer from a flat plate, I can take a finite set of such coefficients, truncated at a particular value. That value will of course depend upon the accuracy that I want for the series. Okay. The infinite series gives you the exact solution. You can get a good numerical approximation by truncating this solution at a finite set of basis functions. Okay. So, the procedure is exactly parallel to the procedure for the flow past a flat plate, okay, except that the differential operator is slightly more complicated. Instead of d square z by dz square that I had over there, I have 1 by r d by dr of r, partial of capital R by partial r. And because of that, the solutions are not simple sine and cosine functions, they tend out to be Bessel functions. Nevertheless, the Bessel functions have all the orthogonality properties and other properties that we require in order to be to obtain all of the coefficients in this expansion. Okay. So, this summarizes the solution of separation of variables in cylindrical coordinates. Many problems in cylindrical coordinates can be solved this way. They always have the operator 1 over r d by dr of r times d t by dr is equal to the unsteady term, and because of that you will always get solutions of the type of Bessel functions. Okay. So, let us go on to the next problem, which is a technologically important problem, okay, the flow in a pipe. So, in this case, if you have a cylindrical pipe, this is the axis of the pipe, okay, you apply a pressure difference across the ends of the pipe. Okay. So, let us just call this as the z axis, this as the r axis, the radial axis. There is a pressure difference applied across the ends of the pipe, okay, and that results in a pressure gradient along the pipe. At each distance z, as you go downstream, the pressure keeps decreasing, okay, and that pressure gradient is responsible for the flow field. So, as you probably know, the velocity profile in the pipe is a parabolic velocity profile. This is a parabolic flow, okay. And our task is to use momentum balances to calculate this parabolic velocity profile. Okay. So, this is a problem in momentum transfer. Okay. A pressure difference applied across the pipe generates a flow through the pipe. Okay. So, how do we solve this problem? As usual, we take a cylindrical shell. Okay. A cylindrical shell of inner radius r and outer radius r plus delta r. Okay. So, if I look at it from the side, I will see something like this. This is the inner radius r, this is the outer radius r plus delta r. Okay. And of course, there is a distance delta z here between z and z plus delta z. Okay. Delta z is the distance along the axis, delta r is the difference, okay, between this right road. So, this is delta z, the distance along the axis between two locations z and z plus delta z. Okay. And this is the annulus between two locations r and r plus delta r. So, we will write a momentum balance equation for this cylindrical shell. The velocity is only in the z direction. Okay. There is no velocity perpendicular to the wall of the pipe. So, the velocity in this case is only along the z direction. Okay. So, you will write a momentum balance equation for the velocity in the z direction. In other words, we are writing momentum balance equation for the z component of the momentum. Okay. Momentum balance. Okay. Rate of change of momentum is equal to sum of applied forces. What is the rate of change of momentum within a time interval delta t? Okay. Momentum in this volume is going to be equal to the density times the velocity times the volume itself, mass times volume. Mass is equal to density times the volume itself. Okay. So, therefore, the rate of change of momentum is going to be equal to rho times V z at r z t plus delta t minus rho V z at r z t times the volume. Volume in this case is the volume of this cylindrical shell. So, this is equal to this cylindrical cross sectional area times the distance. Okay. 2 pi r delta z. Okay. So, this is the change in momentum within a time interval delta t. The rate of change of momentum is this whole thing divided by delta t itself. Okay. So, that is the rate of change of momentum. Okay. What about the applied forces? Let us go back to looking at the cylindrical volume. This is the axis of the cylindrical volume. Okay. There are applied forces, there are shear stresses acting on these surfaces. Okay. There are shear stresses acting on these surfaces. They act not only on the outer surface, but also on the inner surface. Okay. They act not only the outer surface, but also on the inner surface. Okay. There are shear stresses acting on these two surfaces. Okay. So, therefore, the shear forces is going to be equal to the shear stress times the area of the cylindrical surface. Okay. Shear stress is, okay, I define tau ZR is equal to force in z direction at surface with unit normal in r direction. Okay, so that is the component of the shear stress tau z r. I am writing a momentum balance equation for the z component of the momentum. Therefore, I have to consider the z component of the force in z direction. Okay. The cylindrical surfaces have unit normal in the r direction. The normal to this surface is in this direction. Okay. The outer surface, the outward unit normal is in the plus r direction, it goes outwards. At the inner surface, it is in the minus r direction. Okay. If I look at the two cylindrical surfaces like this, side on, the outward unit normal is outward. For the inner surface, the outward unit normal is directed towards the center. Okay. So, therefore, the shear force at the outer surface is going to be equal to the shear stress times the area. Area in this case is 2 pi r delta z. 2 pi r is the circumference, delta z is the thickness. So, that is the area. Okay. This at the location r plus delta r. Okay. So, that is the shear force acting on the outer surface. As I said, on the outer surface, the unit normal is directed outwards. Okay. At the inner surface, the unit normal is directed inwards. Therefore, the force acting along the inner r direction is going to be equal to minus tau z r into 2 pi r delta z at r. Okay. So, this is the force acting on the surfaces, the outer and the inner cylindrical surfaces for this differential volume. However, I also have a pressure gradient within the flow. That means that the pressure acting on this surface is not the same as the pressure that is acting on this surface. That is because there is a gradient in the pressure as you go downstream. Okay. So, therefore, I also have to include the pressure forces. Okay. There is a pressure force that is acting along the plus z direction at the surface at z. This is at z, this is at z plus delta z, and this is the thickness delta z. Okay, so, there is a pressure force acting in the plus z direction at the location z. Okay. This is given by the pressure times the area. Area in this case is the annular area, okay, where the pressure force is acting between the two cylinders. Okay. This has to be 2 pi r times delta r, okay, at the location z. Okay. So, that is the pressure force acting in the plus z direction at the surface at z. Okay. At the other surface, there is a pressure force acting in the opposite direction, because pressure always acts inward, okay, on a volume. Okay. So, the pressure is acting in the minus z direction. The net force exerted by that pressure acting in the minus z direction is minus p times 2 pi r delta r at z plus delta z. Okay. So, these are the two forces, the shear forces acting on the cylindrical surfaces parallel to the surfaces, pressure forces acting on the annular surfaces perpendicular to the surfaces. Okay. So, these two together account for the rate of change of momentum in this differential volume. Okay. So, putting all that together, okay, rho times u z at r z t plus delta t minus rho times u z at r z t times 2 pi r delta z divided by delta t. Rate of change of momentum is equal to the sum of the applied forces. is equal to tau ZR into 2 pi r delta z at r plus delta r minus tau ZR 2 pi r delta z at r plus p 2 pi r delta r at the location z minus p 2 pi r delta r at the location z plus delta z. So, that is the final momentum balance equation, and as usual we divide throughout by volume, divide by 2 pi r delta z, okay, divide by the total volume. Okay. So, once I do that, I will get rho u z at r z t plus delta t minus rho u z at r z t by delta t is equal to, in this case now one has to be careful. Okay. I have r here at r plus delta r and r here at r itself. Okay. These two, at these two locations the radius is not the same. Therefore, I cannot divide throughout by r, because the radius here at r plus delta r is different from the radius here at r. Okay. Therefore, if I divide throughout by 2 pi r delta z, what I will get is 1 by r 1 by delta r into tau r z into r at r plus delta r minus tau r z into r at r. And plus the second term, it is calculated at the average radius. So, that is the same for the inner and the outer surfaces. Okay. So, here I will get p at z minus p at z plus delta z by delta z. Okay. And if I take the limit delta t delta z delta r going to 0, these difference equations reduce to differential equations. Okay. So, this becomes rho times partial u z by partial t is equal to 1 by r t by dr of r tau z r, and this term here p at z minus p at z plus delta z by delta z. P at z plus delta z minus p at z is dp dz, but I have p at z minus p at z plus delta z. So, this is equal to minus partial p by partial z. Okay. And I should make a small difference. So, this is my equation. Okay. This is the analog of the, this is the momentum flux, this is the analog of the heat and mass flux. Okay. Similar to what we had in the case of the heat transfer and the mass transfer problem. However, I have an additional term here which is a pressure gradient. This is special only to fluid mechanics. It does, there is no analog for the pressure gradient in heat and mass transfer. Okay. In order to get a differential equation for the velocity, I need to write down the shear stress in terms of the velocity gradient, Newton's law of viscosity. Okay. Is equal to mu times partial u z by partial r. Okay. And with that, I will get rho times du z by dt is equal to 1 by r t by dr of r du z by dr minus dp by dz times the viscosity mu. Okay. Note that this part of it is exactly identical to what we had in the case of heat transfer. Okay. If I divide throughout by the density, I can write this in terms of the kinematic viscosity. duz by dt is equal to nu into 1 by r d by dr of r duz by dr minus 1 by rho dp by dz. Okay. So, this part of it is exactly identical to what we had for the temperature field, except that I substituted uz for the temperature and nu kinematic viscosity instead of the thermal diffusivity alpha. Okay. However, this pressure gradient is now different. Okay. This is special only to fluid mechanics. So, this is the differential equation for a flow with a pressure gradient in it. Okay. How do I solve it? Simplest case first, steady state. duz by dt is equal to 0. Okay. And therefore, I will have mu 1 over r d by dr of r duz by dr is equal to dp by dz. dp by dz is the pressure gradient along the axial direction. Okay. This equation can be integrated to find out what is the velocity profile from the consideration that the pressure is independent of the radius. That is, as I go across the tube, there is no net change in pressure across the tube in the radial direction. Okay. I will show you later that that is an exact result. Okay. For that, you have to write down the momentum equation in the radial direction. That momentum equation in the radial direction will contain similar terms. There will be terms that depend upon the velocity. There will be one term which contains dp by dr. However, the velocity ur is identically equal to 0. Okay, the velocity ur is identically equal to 0 at all points. We have velocity only in the z direction. Therefore, dp dr has to be equal to 0, because it is not balancing any viscous stresses. Okay. You not have a pressure variation in the radial direction, it has to be balancing some other stress, and there is no other stress to balance. Therefore, the pressure is a constant across the radius of the tube. Okay. So, with that I can integrate this. Okay. I will get d by dr of r duz by dr is equal to 1 by mu dp by dz into r. Okay. And therefore, r duz by dr is equal to 1 by mu dp by dz r square by 2 plus a constant C1. Okay. And duz by dr is equal to plus C1 by r. Okay. Integrated a second time to get uz is equal to 1 by 4 mu dp by dz r square, okay, plus C1 log r plus C2, where the constant C1 and C2 are to be determined from the boundary conditions. Okay. So, let us look at what are the boundary conditions for this problem. Okay. One condition, of course, is that at the wall of the tube, okay, at r is equal to r, the wall of the tube, I require that the velocity has to be 0, because the wall is stationary and the fluid velocity has to be equal to the velocity of the surface at the wall. Okay. I require that uz has to be equal to 0. Okay. So, that is the boundary condition at the surface, okay, at r is equal to capital R. How about at the axis itself, at r is equal to 0? Okay. Just I had argued to you earlier that symmetry requires that dt dr is equal to 0 at the axis. Okay. In this case itself, at r is equal to 0, symmetry will require that duz by dr has to be equal to 0. There is a slope of the velocity at the origin itself it has to be 0. Otherwise, as you come from different sides, you will get different slopes for the velocity as you approach the center. It is possible to have that provided there is a net stress exerted by some object at the center. In this case, we have no object at the center, it is just a pipe. Okay, there is no surface at the center. Therefore, the velocity derivative has to go to 0 at the origin itself. Okay. So, the boundary conditions u z is equal to 0 at r is equal to capital R, and du z by dr is equal to 0 at r is equal to 0. Okay. From this equation, you can easily see that du z by dr will be 0 only if C1 is equal to 0, otherwise it goes to infinity. Okay. So, the symmetry condition requires that C1 is equal to 0 at r is equal to otherwise the velocity will be infinite at r is equal to 0 at the axis of the tube. Okay. So, C1 is equal to 0 and C2 can be determined from the condition that u z is equal to 0 at r is equal to capital R. Okay. And my final equation for the velocity becomes u z is equal to minus 1 over 4 mu dp by dz into r square minus r square. Okay. So, this is the final expression for the velocity field, okay, for the flow in a pipe. Okay. This is called the Hagen-Poiseuille flow for the flow in a pipe. Okay. And I can also write this as u z is equal to minus 1 over 4 mu r square. I am sorry. 4 mu dp by dz into 1 minus r by r the whole square. Note that the velocity is positive when the pressure gradient is negative. In other words, dp by dz has to be negative. Pressure has to decrease along the length of the tube for the velocity to be positive. Okay. And therefore, the pressure gradient and the velocity have opposite signs. Okay. Because I need to have a higher pressure at the inlet and a lower pressure at the outlet in order for the velocity to be positive. Okay. Now, one can calculate the total flow, total mass flow, okay, due to this velocity profile. Okay. The total mass flow Q is equal to rho times integral, okay, of u z times r dr. Okay. Okay. So, basically what I have is a pipe of certain cross section, okay, and I am calculating it has a certain velocity profile, okay, and I am calculating the integral of u z times the differential area. Okay. Because if I look in a cylindrical coordinate system, okay, the differential area between two annulus is going to be equal to 2 pi r times dr. Okay. So, integrate 2 pi r dr, okay, let me just remove this. Into 2 pi. Okay. So, I can calculate that to get a a mass flux which Q is equal to pi r power 4 by 8 mu into dp by dx, okay, with a negative sign. Once again, because dp by dx is positive, the flow is positive in this direction. Okay. And I can calculate the average velocity from this. Okay. The average velocity q z bar is equal to q by pi r square, okay, is equal to minus pi r square by 8 into dp by dx. Okay. Go back to this expression. Okay. The maximum velocity is at the center where r is equal to 0. Okay. The maximum velocity is minus r square by 4 mu times dp by dz. The average velocity is minus r square by 8 mu, okay, dp by dz. Therefore, this is equal to uz maximum by 2. The average velocity is half the maximum velocity for the flow through a pipe. Okay. Next step, we will determine the relationship between the friction factor and the Reynolds number from the solution that we have just calculated. We will get our result that FRE is equal to 16, that F is equal to 16 by RE for this particular case. Okay. So, since we are out of time, we will continue that in the next class, and then we will look at a slightly more complicated situation, that is an oscillatory flow in a pipe. Okay. So, we will continue this in the next lecture, since we are out of time right now. Thank you.